Okay, let's start by looking a little bit at Twitch. Most of you should know Twitch by now. Twitch website looks like this, and you have something like channels. So each user gets a channel where they can stream video, mostly gameplays with an audio comment and maybe the face of the streamer somewhere in the image. Let's go to this stream, for example. And we have the stream in the middle, and people or other users can react to the stream by writing chat comments. There are people that are subscribed to the channel, so they get some badge, and they can react to this to the events in the stream by writing comments and using so-called emotes that have a text representation that they type into the chat window, and then it gets converted into this kind of image. Okay, so this stream has now 3,000 users watching, and the chat is somehow slow, so to say. Some other streamers have a lot more traffic on their chat. So sometimes it's a little bit hard to follow what people are writing, and so people write mostly very short comments and have a very internet-based slang, but more to that later. Okay. Let's go into Twitch in general. Twitch is a video game streaming platform that was launched in 2011 and became the most popular game streaming platform, and then was bought by Amazon in 2014. Yeah, and Amazon connected it to their Prime service, so people can subscribe when they have a Prime subscription at Amazon. They can subscribe to one channel per month for free. So this helps streamers because they can get money from Amazon directly, so to say. Okay, Twitch in numbers. We have around 2 million concurrent viewers at every time step, watching around 90,000 concurrent streams in more than 30 languages. Since Corona, so since March, the traffic went up to more than 1.5 billion hours of stream watched per month by the users. We have 1 million unique daily streamers and 7 million active streamers, so a large user base that produces content, and even more people producing chat comments. So at the end of the month, we have around 1 billion public Twitch chat comments to work with. Twitch tries to make money by selling subscriptions to channels. So users can subscribe, as I just said, to certain channels to support their favorite streamer by paying $5, $10, or $25 a month. And they benefit from this by getting some digital goods, for example, an ad-free viewing experience, at least before the stream starts. Inside of the stream, there are sometimes advertisements as well that are not filtered by the subscription model. They get exclusive access to some chat rooms and this badge that I showed you earlier. And they also are able to use subscriber-only emotes, so emotes that are exclusive for this channel and for subscribers of that channel. So this business model, even though the numbers seem to be very high, to pay for a monthly subscription to just support one streamer, it seems to be very lucrative, because if you look at only the top 20 channels, they generate more or nearly $800,000 dollars per month through subscriptions alone, which does not include any advertisements before or during the streams, or some sponsorings that streamers usually do with some game developers, for example. The money that comes to Twitch from these subscriptions is then split 50-50 to the streamer and to Twitch. So each one, the streamer and Twitch, have motivation to get people to subscribe to channels. So since research is mostly where the money is, Twitch became a research subject in the last few years in various research fields, mostly to understand the platform and to get more revenue by the users. For example, research questions are: when and why are users watching? To know how to get them in front of the screen more often. What games do users like to watch? To give feedback to game developers, for example, to make it more appealing for users watching the game. How do chat users interact with each other? For example, to get better spam detection filters. Do users like what they see? For example, by understanding what kind of content people produce in the comments. And do subscribers behave differently than non-subscribers in chat, which is the main question we wanted to ask in this challenge. There are definitely different research fields that could be applied to, for example, natural language processing or image or audio processing, like if you want to use the video in your research, you can use recommender systems to recommend channels or something like that. Graph analysis to understand the connections between users and channels, or social studies to understand the platform in general. So, as I said, the question for this task and discovery challenge was: do subscribers behave differently than non-subscribers in the chat? So the task was to build a binary classifier that predicts the subscription status of users in Twitch channels given their chat messages. What is this good for? If we have such a subscription classifier, we can take a bunch of not subscribed user channel combinations, put them through the network or through the model, and for the users that the subscription classifier misclassifies them as subscribed even though they are not subscribed, we can use targeted advertising, for example, because the model learned some kind of behavior patterns that make a subscription interested user. The follow-up question to this would be: do unsubscribed users who are misclassified as subscribed to a channel make good targeting targets? So this would be another research question for the future. But now the task was to build such a subscription classifier. And to do that, we need to understand how Twitch and the chat works. So as you could have seen in the screen share by now, the chat messages are relatively short. They have lots of emotes and internet slang and gamer slang, which is mostly the same. But also they use many all caps messages, as well as have grammatical and orthographical mistakes. If we look at the words that are mostly used in the Twitch comments, we can see that emotes like PogChamp or LUL are very often used. And in a recent paper that we published, we did this a little bit more thorough by looking at the top words of Twitch and the common English language and Twitter. And we found that emotes are very crucial to Twitch's language. And even if we remove all emotes from the top words, we get many words that are not present in the common English or even in the Twitter domain. So Twitch's language is fairly different from common English or Twitter. Because emotes are there and are a crucial part to the Twitch language, we thought that they might contain some meaning and are used in some special scenarios. For example, to express emotions, as the name says. So we were able to train a word-to-vec model on Twitch messages and applied some vector calculations. You may know the classic word-to-vec example that a king minus a man plus a woman equals to a queen. So what we did was looking at two emotes, lul and omega lul, which are clearly the same emote, but the mouth of the lul emote is enlarged. So basically this is an intensification of this emote. So we used this representation and relation between those representations to apply them to other emotes. For example, feels good man, which is a very happy emote, becomes a feels amazing man, which is even more positive. And feels Batman, which is a sad emote, becomes paper hands, which is a crying emote, and so on and so forth. So we were sure that emotes capture meaning, and even and because Twitch has lots of emotes, we used these emotes to build an emote lexicon or emote sentiment lexicon, to say better. So we took the top 100 Twitch emotes and gave them to Twitch users to label them as either negative, neutral, or positive to get emote sentiment lexicon. And then we were able to build a sentiment classifier for Twitch messages. So we were able to give real-time feedback to streamers, or in general analyze streams in real time, how different events were perceived sentiment-wise to on the audience. So in this paper we published recently, we used natural language processing and tried to answer the question, do users like what they see? In this challenges task was the question, do subscribers behave differently than non-subscribers in chat? So what we did, we also scraped Twitch messages, in this case more than 700 million public Twitch comments from January 2020, including some metadata like timestamp or the game that was played during this comment was posted. We pre-processed this by only using channels that were labeled as English, and removed all user channel combinations for that the subscription status changed. So if a user subscribes or unsubscribes from a channel in January, we removed that. We then split the data set into a training and a test set. While the training data set has more than 400 million comments and 29.5 million user channel combinations, the test set comprised of 90,000 user channel combinations. You can download both of these data sets on the Challenges website, so if you're interested to do more research in the future, you're welcome to do that. One thing to notice is the test set sampling. We categorized each user and channel into low, normal, and high activity groups, and sampled 10,000 user channel combinations for each of these activity group combinations. So in the end, we sampled 10,000 user channel combinations for low users together with low active channels, up to highly active and highly active users and channels. Additionally, for 50% of test users, we removed all comments from other channels in the training dataset. So we were able to analyze how models handle different users and channel activities and new users. We gave this dataset out in March, I think, and participants had 3 months to complete the task. We had 23 team registrations. But in the end, sadly, we only got 4 model submissions over Tira and 3 descriptive papers. We're not quite sure why this drop happened. There are some things that we can consider. For example, maybe the dataset was too large to handle, or maybe everyone was in home office during that time and was not able to get to a powerful machine, or we haven't advertised the challenge enough. So the results of this challenge are as follows. We had 4 submissions. 3 of them had a paper, so we wanted to know what the team It's time did, because the runtime was very short. So we looked at the code that was submitted to Tira, and they exploited some shortcomings of our dataset. Their idea was that subscribers can use subscriber-only emotes of channels. So they extracted subscriber-only emotes from the training dataset using a heuristic and tried to find these emotes inside of new users in the test set if they posted into the channel. So the precision was fairly high in this case, but the recall was fairly low. Overall, we used the F1 score to weight both of these metrics in one number, and thus Team voyTECH won the competition, but all of the participants beat the random baseline, which samples from the training class distribution. So in the end, the winner's podium looks like this. Because It's time cheated, they were disqualified afterwards, after the challenge ended. And so on this 3rd place, Team StinkyCheese, on the 2nd place, CoolStoryBob, and on the 1st place, voyTECH. So congratulations to all of you to make it to the winner's podium. Now let's start with the talks and the question and answering sessions. We will go through this by looking at the full pre-recorded talks, which are 15 minutes, and afterwards we have 15 minutes of questions. If you have questions, you can write them in the Zoom chat, the Hoover Q&A section for this session or for the respective session, or raise your hand in Zoom and unmute. So we did this as a Zoom meeting instead of a Zoom webinar because we wanted to have easier controls to start discussions and not have one person to unmute everyone. So you're free to unmute yourself if you want, but maybe it's easier sometimes to just write the question in the Zoom chat. Okay. Then let's begin with Team voyTECH, 1st place. Does everyone see the webpage? Okay. Okay, let's start.
Hi everyone. and thanks for the opportunity to talk about our approach to the Discovery Challenge. My name is Emanuel, and this is joint work with Anastasios. First, we need a high-level conceptual understanding about the problem that we want to solve. Only then can we choose a concrete representation and a machine learning model that works well with this representation. Only then can we run experiments which hopefully help us to understand our model better and learn more about the problem that we want to solve. In the following, I'm going to go over our work exactly in this order. First, modeling user activity, relationships over content. We first asked ourselves, what happens on Twitch? Twitch is a video game live streaming service where a user can join channels and video games are streamed on these channels. One key feature is that user can comment on these streams in real time. Our task is to predict if a specific user is subscribed to a channel. For this task, we have 700 million public Twitch comments published during January. On the slide, you see a snippet for a specific channel user combination containing a list of messages. Each of these messages is timestamped. We have also the information about the game played in this channel. Another aspect of the dataset I want to draw attention to is that the channel user can be grouped by their activity. This is important because in the evaluation protocol, these channel user activity groups are equally weighted. This is important because in the training data, these channel user activity groups are appearing in vastly different proportions. Having seen both the user-facing representation of our problem and the data that we have available, we can draw a simple graph where a user subscribes to a channel, a game is hosted by a channel, and the user watches a game. By looking at the data in this way, we can clearly see the relationships that we have. And this is something we're going to focus on. One especially important aspect is that the user is indirectly connected to a channel over game. This is important, as we'll see later, because for some of the users, especially for the users with little history, going over this game helps us to generalize better. Okay, having this representation or this view on the problem, our task is now to create user features and channel features from the message log data that we have in such a way that it generalizes well. Just using the user ID and the channel ID wouldn't be sufficient. Next, we will look at different ways how these features can be created and how they can be represented. An additional point I want to make is that we didn't use the message text at all. We could have included it in as spec of words or as word embeddings, but we wanted to really focus on the relationships instead.
Part 2, target encoding. Why we choose boosting trees as our model. Instead of operating on our graph representation directly, we use it as motivation for our feature engineering. We therefore have a binary classification problem with 3 different sets of features.
The user's features, for example, represent properties of the user, like the game he is most interested in, how active he is, or also just his user ID. We can derive similar features for the channel. In addition, we have user channel specific features. For example, how many messages a user has posted in a specific channel, or how many characters he has posted in this channel. So we end up with a fair amount of categorical variables due to the IDs that we use in the feature engineering. We know that preprocessing with one-hot encoding is difficult for tree-based models. So the question is, can we do better? Popular implementations like CatBoost and LightGBM handle categorical encodings internally. On Kaggle, a technique called target encoding has been very popular in this setting. Is there a connection? Let's see.
Categorical features are very important for this competition. In general, machine learning models cannot handle categoricals natively. Therefore, there are many well-known techniques for encoding categoricals, like one-hot encoding, label encoding, feature hashing, etc. Here we will focus on what is called as a target encoding. Let's define what a mean target encoding is. Consider the following example, where you have a zip postal code categorical and a binary target variable. Mean target encoding is simply defined as the average value of any category. For example, here, depicted in red, you see the category 30XX, whose average value is 1/3. So in this case, mean target encoding replaces the zip category with a zip_empty feature. Notice that this feature now is numeric, so we can input it into any model. There is one important issue with mean target encodings, and this is the usage of target values. Using target values in feature extraction can cause target leakage. So regularization is very, very important. There is a connection between mean target encodings and tree splits in boosting trees. There are two libraries for tree boosting. One is called CatBoost and the other LightGBM. In CatBoost, mean target encoding happens before the tree splits. So all the categoricals are encoded using mean target encoding before the tree splits. Whereas in LightGBM, the mean target encoding happens on each tree split. We chose to use the CatBoost library for this competition.
So by now we have abstract understanding of the problem. We have concrete representation in form of high-dimensional categorical variables, and we also made really sure that this representation works well together with our model. Now it's time to actually look at some concrete results. On the slide, we have some additional experiments which show us two aspects. And the first one is, if you look at the red braces, the top red braces, we can reduce the feature set from all features to top features without losing much performance on the myTest split. And by reducing the interactions from second order to first order, that's the max control complexity column, we see quite a drop in performance. So this at least indicates that we have a strong set of core features, and that having this interaction, which is equivalent to modeling relationships, is important. Let's now have a look at the feature importance to see if we can gain some more intuition about our problem. what we can see is that by far the most important feature is the channel ID, followed by the user ID. That's interesting because from the recommender systems literature and research, we know that IDs are capable of aggregating lots of information. The difference between the user and the channel ID is likely due to the fact that we have no history for many of the users. And seeing that the G-top aggregated for specific users, so the top game, that plays a huge role, I think gives credibility to what we have seen in the beginning, or the idea that we can reach or connect the user on the channel by going over the game. All the features in blue basically different indicators for activity. And I think it's not too surprising that channel which is not very active, or a user that's not very active, that we see less subscriptions for both of them. The last point I want to mention is that we saw quite some resource consumptions in the CatBoost model that we trained. In concrete, we haven't been able to use higher than second order interactions. We used a machine with 100 gigabytes RAM and a powerful GPU, and still were like really hitting the limit. Our best model had a disk size of over 30 gigabytes and a peak RAM during training of 70 gigabytes. I think that's all quite a lot, considering the data set that we used. And it seems quite likely that that we have some opportunity for optimization here, especially exploiting the structure in the design metrics or in the feature that we used. Seems quite promising. To sum it up, we have seen that we can formulate the problem as a simple graph, and we can then use categorical variables to concretely represent this problem, and use boosting trees effectively to achieve great prediction performance. I hope you found this interesting. Please feel free to contact me if you're interested in academic or commercial collaborations. Thank you.
Okay. Thank you very much, Emmanuel and Anastasios. Great talk. Now you can unmute so we can ask questions. And if there are any questions, write them in the Zoom chat or just unmute and ask them if you want, however you like.
Hello, I have a question. First of all, congratulations for coming in first. You pointed out at the beginning of your talk, you pointed out an important point, which is that we have actually what you would call a covariate shift. There's a difference in the distribution between the training set and the test set. So we saw that as well, but we didn't resample the training set. Because we were quite sure about the resampling process. Did you do that, just out of curiosity? Did you resample the training set in any way to get an identical distribution?
No, we didn't. Can you hear me?
Yep. Yeah.
Yes. Okay. No, we didn't, because the training set was already quite big and resampling didn't feel like the right way, especially since the distributions are really that different. So what we did instead is we created a test data set, let's call it dev data set, which really represented the leaderboard. So that at least when tuning the models that we have similar scores on the leaderboard. So this way, at least we can somehow correct for this covariance shift, or at least we know what the effects that it creates.
Okay.
Did it make sense, or?
Yeah, in other words, your validation set has to follow the test set in terms of statistics. So that's what we did.
And ideally, that would also be the case for a training set, but yeah, that's something we didn't do.
Okay, I think we have another question from Tulio. You can just go ahead and unmute yourself.
Yeah, first of all, congratulations on reaching the best results in the challenge. You mentioned that you made some tests with a subset of the features. What were exactly the top features you selected? Just the ones in that graph?
Well, it's in the paper, to be honest. I don't remember from heart,
Oh.
but I think the important message really is it was like the expected as the user ID, the channel ID, like the standard that you expect from recommender systems, and then
the identification.
And then the ID for the game. And it's not exactly true, because all these activity features lumped together are also quite important. But I think there's like I mentioned in the talk, I still like surprise or insight there, because it just shows you how active a user is. Unless I would at least guess less about his inclinations in detail.
Thank you.
Okay, then Martin was next.
Yeah, thank you. I wanted to know, since you mentioned that you did not use the text at all as a source for features and information, did you at all experiment with adding it to your classifier, either building a second one and building an ensemble, or even integrating it into the existing classifier?
We didn't. Maybe it's a bit too harsh to say that we didn't use it at all, because I mentioned it like we used like the amount of text basically posted as a feature. Mm-hmm. So implicitly we somehow used the text, but really we didn't use the words or the icons itself. And we haven't done experiments on that.
Okay, interesting.
Maybe.
Oh, sorry. Go ahead.
Yeah, maybe also the reason why we didn't do it. Time constraint for sure, but also from recommender systems, again, we know that as soon as you have a fair amount, probably, I don't know, it's hard to guess, depends on data set, but 8 to 10 feedbacks or something, you can approximate the attributes of user movies or whatever you have pretty well. So that's basically the motivation why we didn't dig into that too much.
Thank you.
I had a question on the features that you identified to be most important, which was the channel ID and the user ID. So I remember they were among our most important features, but I was wondering if you learned from the training set, basically which user is in which channel, you can try to generalize in order to classify the test set. But as far as I remember the test set, there were 50% of the users that have been seen, and 50% of the users were new. So did you experience any differences there? Or did you not directly use it as saying this user is in this channel, so I will take this over to the test set? Maybe I haven't fully gotten it. I haven't read your paper yet.
Okay, try to take it apart. So we use the user and the channel ID, but we don't use the combination. So for each pair, I use the. So we don't create like joint features for the user channel combination, because that's I think unique in the training set. That doesn't generalize, but we use the user ID and the channel ID. And I think the key really is to use the game ID as well, because if you think about it, many users really, or it's more extreme for the channels. Many channels really have one favorite game basically, and if you have one favorite game, you're probably similar to another channel that also like supports this game a lot. And that again, that generalizes really well, and that's something you can learn from the training data set. I'm not sure if that's exactly matching the question, but
yes, thank you. Very good. Thank you. I've got it now.
Okay. Yeah, I thought this game ID thing was very interesting, because does that say that certain games are more likely to have people subscribe to the channels that they that stream these kind of games? So, for example, do people like to subscribe to channels that stream Counter-Strike or some other games more than to, I don't know, any other game that is not so popular, for example?
Yeah, I can totally agree on that. The game title also played a crucial role in our approach. If we looked at the feature importance, so the game did play a role for sure.
yeah, I also agree that by using the game ID, you're probably capturing this kind of biases in the data, basically. That's a concept you just mentioned.
Mm. To you?
Yes, I also noticed that you use the feature to identify when a user was commenting on a just chatting category. I thought that was a really interesting take. Do you think it has some ways to improve on that idea? Because it really seems intuitive that it would indicate if a user wants to be subscribed or not.
Okay, yeah, you got me there. So this is basically the one time where we actually tried to use the text itself. So in this sense, we actually did. And it did help. So that was the one and only attempt where we tried to, we thought it's really smart, and yeah, didn't help much, to be honest.
Yeah.
Maybe there are better ways, but we didn't find them. Or we also stopped looking.
Yes.
Okay. If there are any other questions in the chat or
In the Zoom chat, there are none, and I don't see any in the Hoover chat.
Okay. However, the Hoover chat is very strange because there are sessions for each of your talks, and sometimes people write the wrong questions in the right sessions and so on. Okay. Okay, thank you again, Emmanuel and Anastasios, for this talk about the winning submission. Now we are going to the next talk, which is Team CoolStoryBob. Marvin will talk, and afterwards, Marvin and Andreas, I think, will both be open to questions.
Hello everyone, my name is Marvin Gartner. I'm currently a bachelor student at the University of Applied Sciences in Aalen in the field of Business Information Systems. Today it's my pleasure to present Team CoolStoryBob's solution approach to this year's Discovery Challenge. The other team members are Professor Andreas Teisler and Professor Mark Fernandez, both professors at the University of Applied Sciences in Aalen in the field of Business Information Systems. So let's start off with a quick overview of our approach. So the task was to predict the subscription status of Twitch users to a given channel based on their posted chat messages. The motivation behind that was to detect potential subscribers, as Twitch, as well as the streamers themselves, earn more money by acquiring more subscriptions. The dataset included the username, the channel name, as well as the text messages and the streamed games within each channel user combination, and was fully labeled with the subscription status being subscribed and not subscribed. So first, we performed pre-processing of the train set. In the first step, we undersampled the train set as it showed that only 8% of the users were subscribers. We then performed some text pre-processing steps to reduce dimensions and to reduce noises in the train set. In terms of feature engineering, we extracted 3 different feature sets. So the first one being the chat messages itself. We used TF-IDF for that because we figured that the less common a word occurs in the text, the more respective it is to separate the 2 classes. We then extracted the game titles using term frequency plain, as we figured that the more often the game occurs in the text, the more important it is. And additionally, we created some handcrafted statistical features to get more insights of the train set. For classification, we first used column transformer in order to combine all different feature sets that we created into one usable feature set. And then we used 5-fold cross-validation and evaluated decision trees, logistic regression, support vector machines, AdaBoost, and XGBoost. The results showed that XGBoost performed best. This model was also submitted to the Discovery Challenge and achieved 2nd place. In terms of feature importance, we found that games and statistical features that we created were way more important than the chat messages itself, indicating that the chat messages itself are not really good for separating the 2 classes. Outside of this challenge, we think that our model can be used to detect potential subscribers, as the users that were falsely predicted by the model as subscribers can be seen as potential subscribers. All right, so let's continue with a more detailed description of our approach. So first, the train set came in 2 different separate parts. The first one was the train.json, including the channel, the user, and another nested JSON file with the game title, the timestamp, and the chat message itself for every message that was posted in that respective channel user combination. The second file was the train.truth.csv, including again the channel and the user, but this time with the respective subscription status of that channel user combination. So in a first step, we flattened the train.json in order to get every game title and every chat message combined into one new column for each channel user combination. We then took the train.truth.csv and merged the subscription status into that file that we created based on the train.json in order to get one combined train file for further processing. Note that we got rid of the timestamp as we didn't see any usable information from that. Because the 2 files were together about 40 gigabytes of space, we used Spark in order to process these data files. Next, we performed several pre-processing steps in order to reduce noise on the dataset and additionally reduce some dimensions. So the most crucial pre-processing steps were, number 1, undersampling, as the classes were highly imbalanced with only 8% of the users being subscribed. And removal of most frequent and rare words were also pretty good, as they were seen as too much noise in the dataset. And lastly, removal of null values were also seen as a pretty good pre-processing step. With null-valued samples, we only mean samples that didn't contain any values. So that way we got the raw chat messages and transformed them into a structured form in order to be used by classifiers. In terms of feature engineering, based on the train.csv that we created, we extracted 3 different feature sets. The first one were the chat messages themselves, where each distinct word corresponds to 1 feature in FeatureSpace. The second one was the second feature set were the game titles, where each distinct game corresponds to 1 feature in FeatureSpace. And lastly, we created a feature set based on statistical features from the chat messages. Now, if you look at these 2 word clouds that show the most used subscriber terms and the most used non-subscriber terms, we can clearly see that the words used by subscribers and non-subscribers do not really show any differences. So based on that finding, we assume that a word with a lower frequency or words with lower frequency are more likely to represent the class than those with a higher frequency. Based on that, we created a bag of words model based on the chat messages and transformed them into TF-IDF vectorizers, as TF-IDF gives more weights to lower frequenced words than higher frequenced words. We did the same thing for the game titles. So if we look at the games with the most comments by subscribers and the games with the most comments by non-subscribers, we can see that there are shown some differences. As we can see here, the Pokemon game, for example, or the Counter-Strike game are more likely to occur in samples of non-subscribers than in subscribers. Based on that, we assume that the more often a game occurs in the text, the more likely it represents the respective class. Therefore, we created another bag of words model, just like before, this time based on the games, and transformed it into TF vectors, into term frequency vectors plane, because TF gives more weights to words that occur more often. The third feature set were the statistical features that we calculated based on the chat messages. So based on that messages, we calculated, for example, the number of words that a user used or the number of emojis used. But the 2 most crucial statistical features that we extracted were the number of distinct emotes and the number of emotes. Why that? We will see in the next slide. So as a short recap, emotes are Twitch exclusive images or animations that can be posted by users in the chat and provide a quick and wordless expression of their emotions, just like an emoticon or an emoji or smileys, something like that. Now, most of these emotes can only be used by subscribers or by users that show extremely extraordinary activity level in a given channel. So we found that these emotes occur in the text, showing a common syntax that was used for extracting these emotes. So we have an example here of a short comment snippet. We can see that this word starts with a lowercase letter and then continues with an uppercase letter. We found that emotes are represented like this. So that common syntax was used in order to extract the respective emotes. So here we can see the track queue corresponds to this image. These emotes of every text was saved in a separate column, the emotes column, and this column was then used to, number 1, calculate all the emotes that occur in the text, being the emotes count, and then the emotes count distincts represents each distinct used emotes within the text. So let's continue with the training approach. Before initiating the training process, we took the raw data set and we randomly sampled 5 different test sets in order to test our classifier on unseen data later. We then took the remaining train set and resampled and pre-processed it. We trained our mentioned models on that using 5-fold cross-validation in order to generalize the models. And then we tested the trained models using our created test sets in order to see or to get a feeling on how well the classifier will perform on unseen data. Now, another problem that we faced was how to combine the different data set, the different feature sets, in order to get one combined feature set that we can train the classifiers with. So the solution for that was to use scikit-learn's column transformer, which is basically just like a machine learning pipeline that takes features of different types, then performs a transformation, a desired transformation, such as here the chat messages were transformed into TF-IDF vectors and the game titles into TF vectors, and then combines them into one feature space. Then we used another machine learning pipeline that takes the column transformed features, standard scales them, and feeds a classification algorithm with that features. Now, as mentioned earlier, we use 5 different classification algorithms in order to compare different methods. So we used XGBoost, decision trees, logistic regression, support vector machines, and AdaBoost. With this procedure, we trained our final model. So continuing with the results and discussion, the way best model was XGBoost with a F1 score of about 32.3%, outperforming all other alternatives. So we used this model to submit to the discovery challenge, and we got ranked 2nd place with that. Now, if we look at the feature importance of the trained model that we submitted, we can clearly see that the games, as well as the number of emotes and the number of distinct emotes, were way more important for distinguishing the 2 classes than the chat messages themselves. So from that, we concluded that the chat messages themselves did not really do a good job in separating the 2 classes. Rather, the other features that we extracted were just better for distinguishing the 2 classes. So lastly, I want to say some words about how our model can actually be used in a real case for detecting potential subscribers. So given 2 different assumptions, where the first one is that Twitch, as well as the streamers, actually know about who of which user has subscribed to the Twitch channel, to the streamer's channel or not. The second assumption is that a model that can classify a user's subscription status is assumed that it has managed some knowledge of how to tell what user or which users are subscribers and which are not, just based on their chat behavior. So giving these 2 assumptions, we can denote 2 different sets, where the first set is the set of true subscribers, and the second set is the set of subscribers that have been classified by the machine learning model. So based on these 2 sets, we can extract the potential subscribers that correspond to the subscribers classified by the machine learning model, excluding the set of true subscribers. And the remaining set corresponds to the potential subscribers that can be used for, let's say, some targeting advertisement or anything like that. All right, that's it for now. Thanks very much for participating, and I am looking forward for the Q&A session. Have a good one.
Okay, thank you, Marvin, for this talk. Are there any questions?
I have one. If great presentation, by the way. I have a question about using Spark and about your machine learning pipeline. Did you train your models with Spark, or did you do only the pre-processing using Spark and then you move to scikit-learn?
Good question, yeah. So no, we did not train our models with Spark, because Spark offers some machine learning approaches, but it's just not broad enough to satisfy our desires. So no, we only use Spark for the pre-processing, especially for combining the two data sets, because the first one was about 40 gigabytes. So yeah, that's why we used Spark, the Spark framework, for combining the two data sets into one trainable train set. Yeah, yeah, we then used just a short part of the train set, around 2 gigabytes, for training our final classifier, just with using scikit-learn and the standard libraries offered by scikit-learn, just on a local machine.
Yeah. Also, the TF-IDF, I think Spark has these transformers, right? But
yes.
But you did this part on the scikit-learn side.
Exactly. Yeah.
Tulio?
Congratulations on the talk. Very good presentation.
Thank you.
You end up using both TF-IDF for the text of the messages and also TF representation for the games.
Yes.
Doesn't that end up giving you too much of a sparse representation for the data?
Yes, it does give a really big matrix. That's true. It was still possible to train the classifier. So the column transformer I mentioned in the presentation combined the different feature sets into one. So yeah, you're right. It did create a big feature set, a big combined feature set. But using the XGBoost classifier still performed pretty well and pretty fast, even though we used around 650,000 samples. Yeah, so.
I was just wondering if maybe the importance of the text features wasn't that great because of that, but you also use the sparse representation for the games, and that turned out to be the most important feature. So I guess not. Maybe.
Yeah, so first I had doubts on that too, so that when we have one combined feature set, that maybe all the words get a lower importance. But then at the end, so I only showed the top 5 performing features, but if you expand it a little bit, so on the 30th place there do occur some words. So they are still important. Some words are still important for distinguishing the two classes. But as showed, yeah, the way better features were, for example, the emotes and the words.
Thank you.
Okay.
Andreas?
Thanks for the talk. If I understood it correctly, you use the words directly as features. Have you thought about some dimensionality reduction, a kind of embedding or whatever in this direction to reduce the number of features and to make it more coherent or better suitable for this task?
So I'm going to be honest, at that point, I didn't. But as I said earlier, this challenge was the basis of my bachelor thesis. And in that bachelor thesis, I used the cheek square tests in order to identify the most important words. So to answer your question, no, at that point I didn't, because I simply didn't know that's possible.
Okay, thanks. Yeah, I was just curious. There's no problem.
Good question, though. Yeah.
Can you say which are the most important words to identify subscribers?
Actually, no. Right now, no. I'm sorry.
Okay.
I have it somewhere, but I would have to look for it.
But I believe, because I read your bachelor thesis just the other day, I believe the word sub was actually among them.
Oh, right, yeah, true. Sub, yeah. Sub was a very important word, yeah. From the XGBoost feature importance. That's right.
Yeah, because I think that maybe the XGBoost classifier tries to pick up the same strategy as its Boshi time tried to exploit the dataset by looking for channel-specific emotes that are only accessible to subscribers. So this could be something that's what so I wanted to know if it's more like a general word or something very specific to a channel also.
Mm-hmm.
But the question is answered. So Emanuel.
Hi, thanks for the talk. I have a question about the game titles. It sounded like I had a closer look because what we did, we just used them as IDs, and that might not have been a good idea. So do you know if there's some different ways how the same game is written, or are they really like IDs?
So for the game titles, what we did first is we removed the white spaces between the titles so that we have one word, one unique word for every game, and then we transformed it into a term frequency vector so that every game has its unique vector. Does that answer you?
Yes, kind of. So you did normalize the game titles, but
Yes.
was there like, did it make a difference? You probably didn't check. Huh?
No, I didn't check that.
Okay, thanks.
I think they're also a bit normalized on Twitch. So they have the games as categories, basically, if I remember correctly, and that should provide some kind of normalization.
Mm-hmm. Okay, lucky us. Thanks.
Okay, one question by me, maybe. So you said that the less a word occurs, the more it's important for separating the classes. However, if a word is typed wrongly, then it's mostly rare, but it does not yield any information to separate the classes. So have you pre-processed the data such that very less frequent words or words that are very rare are filtered out?
Yes, that's exactly what we did basically.
Okay.
We filtered out the rarest, I think the 10% rarest words, as well as the 5 or 10%, I'm not pretty sure right now, of the most used words. So because they do function as noise in the data set, as you described perfectly.
Okay.
So yeah, we filtered them out.
Nice. Thank you.
Thank you.
So I think it's time to move on. Thanks again, Marvin, for this great talk and for answering the questions. And now, last but not least, Team StinkyCheese, where Tulio will present and afterwards give you the possibility to answer some questions.
Hi, my name is Tulio and I'm representing my team from the Federal University of Minas Gerais in Brazil. Today, I'll be presenting our submission for the ECML-PKDD 2020 Discovery Challenge Workshop. In this work, we propose the StinkyCheese classification model for user channel subscription based on chat messages from a Twitch dataset. Twitch is an online platform in which streaming channels broadcast multimedia content to their audience. Besides the streaming service itself, users can also interact with each other and with the content creators through a channel chat. As part of its monetization model, Twitch offers the purchase of subscription status to channels, and this subscription comes with assorted benefits. In this context, the chat analysis for Twitch challenge consists of building a binary classifier to predict the subscription status of user channel pairs, based on the comments the user made in the channel's chat. Our proposal is a deep learning architecture composed of two main parts. First, an LSTM component that generates a text representation for the chat messages. And second, conversational features extracted from the data, such as the time interval between messages and text length. This model aims to capture both semantic and structural information from the chat data. With only a small portion of the provided dataset, we were able to gain significant insight into the problem, learning some of the complexities and difficulties of using chat data for classification, and defining goals and directions for following research. For this problem, the challenge provides a dataset comprising instances of user channel pairs. Each instance gives the list of all messages a user has written in a channel's chat. This includes not only the text content of said messages, but also the timestamp of each of them, and also the game that was playing in the channel when the user made each comment. With this, the goal of the challenge is to use the chat data and metadata to predict whether the instance represents a user that is subscribed to the channel or not. Our proposal, the StinkyCheese model, aims to use both the text of the user's messages as well as the structure of that user's conversation with chat to predict if it is subscribed to the channel or not. With this goal in mind, we implemented the deep learning model that is composed of two main parts. The first is an architecture based on a long short-term memory network, LSTM. LSTM is an artificial recurrent neural network architecture well suited for tasks that involve sequence data, such as natural language text. This architecture is able to extract long-term dependencies in sequences, making it good at learning high-level information from text. In order to feed the message text through this LSTM, we first concatenate all messages from a user channel pair, so that each instance has a single text sequence. Then, we learn the embedding representations of each token from the sequences as we train the network. The LSTM component then receives as input the sequence of word embeddings from the concatenated messages of the user channel pairs, and returns a vector representation of that concatenated text as a whole. This output can be interpreted as the representation of what the user has said in that channel, capturing the semantic content of the instance. In addition to the LSTM-based component, we also use a selection of conversational features, extracted from the chat data and metadata. These features can be divided into three categories: verbosity, attendance, and participation features. The verbosity features measure how much textual content is generated by the user in the channel. These include the number of messages the user has sent to the channel, the length of the user's concatenated messages in the channel, the average length of messages from the user, and the average length of messages in the channel. The attendance features measure the assiduity and permanence of the user in the channel. This captures the total time the user has spent in the channel between his first and last comments, the average interval between messages for the user in the channel, the standard deviation of interval time between messages, the shortest and the longest interval between consecutive messages. In the participation features, we measure how much the user and channel participate in the dataset. These allow us to take into consideration the perceived popularity of channels and also the involvement of the users. And for this, we use the number of channels in which the user participates and the number of users participating in the channel. These conversational features give us information on the structure of the chat, as well as how the user and the channel in this instance relate to the rest of the training dataset. Finally, once both these components are defined, we concatenate the text representation generated by the LSTM component with the conversational features and run the combined representation through a dense neural network layer. This gives us the prediction of the subscription class as an output. Is the user subscribed to the channel or not? With this proposed model explained, we'll move on to the experimentation setup. For the challenge, we were only able to use a subsample of the original dataset. We sampled 100,000 instances for the training set and another 100,000 for the validation of the model. We preprocessed the data of each of these subsets separately. This includes the conversational feature calculations that depending on comparing one instance to the others. So, for example, when we calculated the average message size in a channel, we find all instances in the 100,000 training sample that involve that channel and calculate the feature based on that. We also experimented with different hyperparameter combinations for the model, exploring the impact of the optimizer chosen for the deep learning model, the impact of the learning rate, and the impact of the text threshold of the text inputs for the LSTM component of the network. That is, the maximum number of words of each concatenated message text sequence. The best overall result was obtained with the Adagrad optimizer, learning rate of 10 to the power of -4, and text input limited to 200 words. In the end, we tested our model on the test set provided by the ChAT challenge, comprising 90,000 instances. Our final submission to the challenge achieved an F1 score of 0.1422, ranking in 4th place. While not getting a result as good as the other participants, we think that we still were able to get some interesting insights into the problem. So let's talk about some of them. One analysis we did was regarding how the accuracy of the model was affected by the activity level of the user being predicted. And here, activity level just gives an idea of how many comments the user writes. So high activity users are those that write many comments, and low activity users write only a few. We divide the test set into instances that represent subscribed user channel pairs and instances that did not. Then we investigated the accuracy our model achieved for either label, subscribed or non-subscribed, according to the activity level. The first graph here at the top shows that for instances in which the user was subscribed to the channel, we achieved higher accuracy predictions when the user had higher activity levels. Meanwhile, the second graph shows that for non-subscribed user channel pairs, our model works better with low activity users. In other words, we tend to correctly predict that high activity users are subscribed and that low activity users are not, and wrongly predict when low activity users are subscribed and high activity users are not. This indicates that our model correlates subscription status with the activity level of the user. A possible research question in the future, for future works, would be, how can we deal with this bias in the model? In order to better visualize the different instances in which the StinkyCheese model was able to correctly predict the subscription status or wrongly predict it, we present a few examples of messages from user channel pairs. So in each of these examples here is a sequence of messages, and each message is separated by the dash. So just looking at the true negative examples for now. That is, the users that wasn't subscribed to the channel, and we correctly predicted that. We have one instance in which the user writes a message to enter a giveaway, and not much for this second example. But when we look at the false negative examples, in which we also predicted the instance as non-subscribed pair, but it was actually subscribed, there is another example that the user only writes a message to enter the giveaway as well. So what's the difference between these two? From these examples, we can see that the task of identifying if a user is subscribed or not based on just the chat is complex. Subscribed users can have interactions in chat as short as those of non-subscribed users, while non-subscribed can have conversations that seem as intimate as a dedicated subscriber. With that, we open several other directions to take this research in. The relation we found between the predictions made by the model and the activity level of the users suggests that it may be taking some features too heavily into consideration. Adding a more complex network structure to find the relationships between the conversational features can greatly improve on this problem. Better feature normalization can also solve some issues. On the text representation side, we can also consider some improvements. Since text from Twitch chat tends to have some very unique tokens, including both culturally specific expressions and token representing emotes, using pre-trained word embeddings from regular text is not ideal. Instead, pre-training word embeddings representation on Twitch-related text can be promising. There's also the possibility of implementing general training improvements, such as better hyperparameter search and better use of the training dataset. In conclusion, we proposed the StinkyCheese model to identify the subscription status of users in Twitch channels. This model combines the text representation of messages learned with LSTM and conversational features to predict whether the user is subscribed or not. We found that the model learned correlation between activity level of user and subscription status, which may have some value, but also represents a bias of the model. With that, we can see that the complexities of the problem open space for future research, and I hope we can see other works in this kind of problem. Thank you, and if anyone has any question, feel free to send me a message.
So thank you, Tulio, and I'm very sorry that the pause button was hiding your face the whole time.
Oh, no problem. Don't worry.
Okay, are there any questions?
I would have a question. So first of all, thanks for the great talk. I have a question regarding your data pre-processing. From your paper, I see that you did remove the stop words.
Yes.
Now, I'm curious, did you experiment with any further pre-processing steps, such as stemming or lemmatization, stuff like that? Or is there any particular reason why you only removed stop words?
So for deep learning techniques, in this case, LSTMs and recurrent networks, we usually don't change a lot of how the words are constructed, because we can use the grammatical and syntactical features of the words to better predict whatever the task we want. So no, we just removed some stop words because we identified that that was working better for our validation sets. But stemming and stemmatization and lemmatization usually don't work for this kind of model.
Okay. Thank you. Very insightful. Thanks.
Yeah.
I may have a follow-up question on this. So when I look at most other forms of social media text, like Twitter or Reddit, turns out that my classification models usually work better if I do not remove stop words, which I hypothesize is that if I have to produce text on a very limited scale, right? So if on Twitter I only have like 280 characters and I want to put a lot of text in there, then I start leaving out words, and my choice of leaving out stop words or deciding not to leave them out tells me a lot about the kind of text I say, right? If I write a news, a breaking something, then I decide to leave out different stop words or reformulate so I do not get over the limit. So it helps me in classification. So if I understand this correctly, the stop words don't really help for Twitch, although Twitch is also the kind of register perhaps where I want to write as short as possible, so my message gets understood quickly in the constant, very fast stream. So maybe that's the question for everyone too. When you studied the text or looked at the messages, did you notice any kind of this where messages or the stop words specifically change depending on the kind of message that the users are writing? Or
Yes,
is it just they leave them out in general? Or?
Very interesting observation. We have seen some works on other kinds of data that do use deep learning models with text that have varied results when either removing or keeping the stop words. So for some data it helps, and for other it doesn't. So we ended up testing both approaches, and for our validation set, it was the results are showing that we should actually remove the stop words. But I'm not so sure about what is the behavior in Twitch chat that leads to this kind of approach being better. So that should be an interesting point to try to look at. If anyone has any insights to that question, feel free to contribute as well.
Well, yeah, otherwise, thank you. So yeah, clearly if the model performs better, right, then there's probably no real correlation between stop word usage and subscriber status. If you leave the stop words out, right, it's less noise, so the model should get better. The only intention I could think of is that people who are subscribed and have some investment in the channel probably tend to write longer text perhaps, or more interactive content because they want the streamer to react, right? So they probably use more stop words then, but then it would be a discriminative feature. But since it isn't, I don't know.
I just looked it up. We did correlation tests between all sorts of features and the subscription status, and we did indeed look at the number of let me see, the number of stop words. Are they correlated with the subscription status? And it's, well, virtually no correlation, a very low figure for correlation. We had it, but it didn't really. Okay, it's the number of stop words. It's not. I'm not sure if you tested leaving them out or leaving them in, but we looked at least at the number. But it really there were no. As far as I remember, there were a handful of features that appeared to be good, but there were many features that, well, contributed somehow, but statistically with a very low number for the correlation value. So it's we were always looking for the treasure. Basically, we were hoping to find a few features that would really make it, but it's I think the problem itself appeared to be not easy to solve. But maybe that I would be personally interested in. The organizers have worked with that sort of data, of course, much longer than we have. If you had tested that and if you had dramatically better results, because all the competitors had, well, looking at the F-score, I would say results that show there's room for improvement, but we couldn't figure out how to improve, I guess.
Okay, Emmanuel, you had a question?
Yes, first, thanks for talk. If I remember it correctly, you subsampled the data quite a bit, the training data. Is that correct?
Yes, unfortunately, yes. We weren't able to use the entire data set for the challenge. So we worked with only a small subsample of it.
Okay, so for us, it was the case, like adding even a little bit more data. So basically the model was improving with the data basically constantly. So I'm just wondering, did you actually do some tests, like how much did it hurt you, or if it did, how much?
We did try to increased the data set a little bit after the challenge. And with only small increments, we weren't able to exactly notice any significant improvements. But we hadn't yet tested with the entire data. So we'll have to see that later.
Okay, I guess could be quite interesting to see how good you perform for users without history compared to the ones with history, because like in our case the prediction dropped quite significantly if you haven't seen the user before. That might not be the case for you, so that could be interesting.
Yes, we did try to check the difference in accuracy with already seen users and users that were new in the test data set. And let me just check here. The results are, I'm pretty sure, yeah, they're in the paper as well. So let me just find it. So for channels that we had already seen in the training set, we got an improvement in the F1 score. But for users that we already had seen, we didn't notice a significant improvement. So for our model, it seems that the channel, already having seen the channel, is the most important part between the two.
This could be an indication that your model is still in the range where it's not really personalizing to the specific user, and that's why you might have to increase the data quite a lot to see a big difference. But it's just speculation. Thanks for the
thanks for the question. We also don't use the information regarding what game the channel was streaming during the user's participation. So that would greatly improve, I believe, this user personification, right? Because if that feature of the game that is being streamed is deeply related to what the user wants to watch, which would indicate what it wants to subscribe to, right? So maybe that could help as well.
And that would be quite intriguing, actually, because it would more or less mean that people just write differently depending on the game they're watching. So, or behave differently in chat.
I would agree that certain games or certain genres of games have evoked different behaviors, excitement, different kinds of excitement, or
different words.
Yes, absolutely,
like
different content words. Yes.
killing in some shooters or so.
Yeah, probably also games that show more skill-intensive gameplay probably evoke different reactions on different occasions, and yeah, that sure seems to be an important part of it.
One thing that I noticed in the results table that is shown now is that your recall is quite high in contrast to the other approaches, which means that your approach has fewer false positives or false negatives? False negatives. So basically, it must have predicted more often that a user is subscribed even though they're not subscribed. So because the training data is so skewed, do you have any idea why this is the case for your model?
Yes, I also noticed that the results table, and I thought it was quite intriguing. I'm not really sure how that works, but I'm not really sure yet. But it probably it has to do with a combination of counting too much on some of the temporal features, right? Because our normalization of the features wasn't done as well as we could. It probably considers too heavily how long the user is watching the channel, which might trigger some too many, which might predict too many users as subscribed. But also the textual content might be muddying the waters a bit. So I don't know, that is a very interesting point to have for future researching.
Okay, thank you. Okay, if there are no questions anymore, are there questions? This doesn't seem to be the case. Are there any Huber questions?
None that I can see.
Okay, so then there is only one thing left. We want to thank every participant for submitting an approach. Thank you that you attended this challenge and this session. I think it was very interesting to have all of you here together to discuss the different approaches, which were very different and very interesting to see how to approach such a complex task. If you have any feedback for this challenge, you can write us a mail or just, yeah, I think a mail is the best way to reach us. I know that I had fun. I hope that you had fun taking part in this session and challenge. And then hope we see us in the near future or in the future somewhere maybe next year or so at ECML. Okay, have a nice weekend and see you.
Thank you, Konstantin, for organizing the session. Thank you.
Yeah. Thank you, everyone.
Thanks very much.
Thanks for the organization to everyone.
Yes.
Thank you.
Also to Albin and everyone else.
Yeah, it was a pleasure. Okay.
It was an endeavor.
Yes. Next time we do a 4 GB dataset, not 40.
Perfect.
Yeah.
Oh, we can provide 400 gigabytes.
Oh, no,
That's
400.
no
Yes, 400. That's what I wanted to say. 400.
Double the data set size every year.
Yes, yes. Oh, great. Let's see how far we go there.
Okay. Have a nice weekend.
You too.
Thank you.
Bye-bye.
Have a nice one.
Bye bye.
Bye bye.
Bye bye.
Bye. Bye bye.